Good morning and welcome you all to this session of the course. So, you see a typical centrifugal fan or blower here. I will show you simultaneously. I do not know, it may be little difficult. Okay, I will try it. Yes, this is the thing. So, let me show you this is the thing. Let me just a minute, let me make these things. Let me show you like this. This is a typical centrifugal fan or blower. Now, centrifugal fan or blower consists of an inlet. This is the impeller, the same principle, impeller which imparts the energy to the fluid. Then after the impeller there is a spiral casing known as volute chamber, spiral or scroll casing. This is the volute where this gains the energy in terms of both velocity and pressure rise at the end of the impeller, high velocity and high pressure. Some of the velocities are then converted in the volute chamber to static pressure depending upon the requirement at the outlet of the machine. So, this is the picture. This can be shown if we take a section like this, then it is this is the impeller, you see it. So, this is the inlet, the flow at the inlet takes place through a nozzle. That means there is a little acceleration of the flow before it enters into the impeller. Now, impeller, it goes radially. It is the same way that it happens in a centrifugal compressor. That means it is sucked or it is induced the axial direction, then the flow change in the radial direction. So, this is the radially outward flow. Then it comes out and this is the volute casing and this is the outlet. So, this is the main component of a centrifugal fan and a centrifugal fan or blower. So, after this I will tell you about the typical type of blades in the in a blower or fan. Now, blower or fan both are the same machines, as I have told, only the static pressure rise is different for blower and fan, and depending upon the flow rate required, the fan blade shape is different. Now, three types of blade shapes from the fluid mechanical principles are used, I tell you. One is known as forward swept blade. You see this left one. What is that? If you consider the motion in this direction, that means this is the direction of rotation. That means the peripheral speed is in this direction, the tangential motion. So, curvature of the blade is in the direction of the motion. This is known as forward swept blade. Another type of blade is known as radial blade. This is forward swept blade, forward swept blade, forward swept blade, forward swept blade. So, this type of blade is known as radial blade. Radial blade. What is the radial blade? Radial blade. Their outlet, that means at the outlet the blade is radial, but at the inlet there is a curvature, and this curvature is forward swept. Why? Because this is the direction of the motion, the curvature in the direction of the motion. So, radial blades are radial outward flat, but it is curved at the inlet which is forward swept. Another is the backward swept, that means its curvature, this is the direction of the motion, its curvature is in the opposite direction of the motion. So, velocity triangles will definitely change, that I will tell you, you can understand, because the direction of velocity and the curvature of the blades are in the opposite direction, or relative directions are changed. Now, before that I tell you, the forward swept blades are used where large flow rates are required, relatively large flow rates and higher pressure rise is required as compared to backward swept blade. Whereas radial blades are preferred where the fluid, that is air used, contains more impurities and dust. This is because of the fact that these are less prone to the blockage and they work more efficiently with the dust laden gas. So, therefore, these radial blades are preferred for that. Now, if we see the velocity triangle, so velocity triangle at the inlet, for example, in the radial you see this is same for all the blades. What is that? There is the inlet velocity is axial, absolute velocity direction, this is the axial direction, axial. This has got no component in the tangential direction, that is VW1 component is 0, VW1 is 0, everything, that is the problem here. VW1 is 0, VW1 is 0, okay, VW1 is 0, you see, that can be seen, VW1 is 0 can be seen, it's seen, VW1 is 0. So, radial blades, so entry for all blades are same, that is VW1 is axial, this is the relative velocity which matches the angle of the blade, this is the peripheral velocity, this makes the vector diagram, that is the velocity triangle. Now, at the outlet also you see, this is the peripheral speed, this is the direction of the flow, a direction of the rotation speed, this velocity, that is the relative velocity, matches the blade angle, that means it is radially outward, and this is the absolute velocity. Alpha 2 is the absolute velocity angle. Beta 1 is the angle of the blade at the inlet, and this is alpha. This is 90 degree, this is the beta 2 which is radial. This is alpha 2 is the angle of the absolute velocity. Now, let us see the velocity triangle for the forward swept blade. The velocity triangle for the forward swept blade is this one, is this one. This is the, it is visible velocity diagram. Let me draw the velocity diagram here. I think for you it will be forward swept blade, I write. So, this is the inlet diagram, it is already same as that, that means there is no tangential component, it is axial, and this is the, now here forward swept, this is the u, the direction of u is this. So, therefore, the direction of u, this is VR1, okay, and this is the u, and this is the VR1, this is the beta 1, okay. VR1 is equal to V1 U1 minus U1, very good, because they differ, it is a radial flow machines, radial outward. Now, at this end what will happen, this will be my radial flow, relative velocity directions, and this will be the diagram will look like this. So, this will be obviously from the VR2, this will be U2 which will be higher than U1, and this will be the V2. So, this is the simple diagram because the velocity is in this direction. So, it has to be like that. In this case, this is defined as the beta 2. That means, in the positive sense U2 is this direction, with this is an obtuse angle. This is this angle beta 2 with the tangent, and this angle is alpha 2. So, this is the velocity triangle which is shown here like this. I think you can see, but this diagram I think is very difficult to see, the things are not properly shown, not legible. However, now for a backward swept, this can be visible. Now, backward swept one, I again draw it here. For the backward swept, what will be that? So, this curvature is in the opposite direction. That means, this is like this. This is in the opposite direction, but the direction of peripheral velocity is like this. So, here also, so this is the same thing, that this is the inlet velocity triangle, okay. This is the inlet velocity triangle, this is VR1, this is V1, let this is U1, sorry, U1, and this angle is beta 1. So, the outlet angle, for example, here or here I can draw the velocity, this relative velocity is this. Then what is this velocity? Relative velocity is this direction, okay, that is VR2. Then this velocity is in this direction, this velocity is in this direction. So, therefore, the absolute velocity will be, so this looks very odd, so little more, the relative, this is U2, this will be V2. So, this will be. Now, if you draw it in scales for a given value of U2 at the outlet and for a fixed value of Vf, you will see that for forward swept blade, the component that V2 is more and the component that VW2, that this one VW2 is much more compared to this is V2, this VW2. So, therefore, you see VW1 is 0, therefore, work done per unit mass is again VW2 U2. Since VW1 U1, VW1 is 0. So, therefore, in this case this is okay, understandable. So, in this case VW2 is more than this, and that is the reason that forward swept blade is used where we require more work and more flow will be available and more static pressure rise will be there. Okay. So, more work will be imparted to the can be imparted to the fluid flowing through it. So, three types of possible blade configuration: forward swept, radial blade and backward swept blades are possible. So, with this, now other treatments I tell you in the axial flow fans and compressors are almost identical to that of the centrifugal compressors which I have told in case of centrifugal blowers and centrifugal fans. Now, with this I will go on solving a problem. Let us see this problem. A centrifugal fan, okay, a centrifugal fan running at 1500, that is 1500 rpm, has inner and outer diameter of the impeller as 0.2 meter and 0.24 meter. That is the inner diameter of the impeller, outer diameter of the impeller. The absolute and relative velocities of air at entry are 20. So, absolute and relative velocities of air at entry are these respectively and those. That means exit, entry and exit absolute and relative velocities are given. The flow rate is 0.6 kg per second. The motor efficiency is 80%. Determine the stage pressure rise, degree of reaction and the power required to drive the fan, assuming the flow to be incompressible with density of air as 1.2 kg per meter. Now, this particular problem I tell you will make your total understanding of the fan or blower clear. So, let us first see that what this problem tells. Now, this problem tells that velocity absolute and relative is given. Now, if you recall this type of problem, what you will do? First you have to find out the stage pressure rise. So, how to find out the stage pressure rise? So, you have to find out. So, first of all you find out the stage pressure rise by which expression? You have to find out the stage pressure rise. Stage pressure rise means what? The total pressure rise in the stage. Okay. So, total pressure rise in this stage depends upon the work done, total work done. If you first find out the work done per unit mass, what is the work done per unit mass? Now, if you remember, the work done per unit mass is VW2 U2 minus VW1 U1. Without going for a change in temperature, stagnation temperature, so far we did. This is because this problem is told that assuming the flow to be incompressible. So, for an incompressible flow, better we do this type of analysis, that this is true for any fluid, incompressible or compressible. If you remember that this work done part VW1 U1, that is work done, that is W by M, can be written as different components. If you remember, that is V2 square, that is work done on the fluid, minus V1 square by 2 plus U2 square minus U1 square by 2, okay, plus VR1 square minus VR2 square by 2. This I explained in details in one earlier class of our fluid machines, that this can be splitted like this from the geometry of the velocity triangles. Why it is required? Because this gives a very clear understanding. This is the gain in kinetic energy where the absolute velocity here in terms of compressor, in terms of pump, in terms of fans, blowers, where the fluid gains energy, V2 is always greater than V1. So, this is the gain in the kinetic energy, this is the gain in the kinetic energy or dynamic, we sometimes tell as dynamic head. It is per unit mass, usually energy per unit mass or unit weight, we call it as head. And this too is the gain in the static head. Why? Why it is called static head or static energy, which is not very much used? That means this is manifested in terms of the increase in the pressure of the fluid. This is because of the change in, this is the change in the peripheral velocity at outer radius and inner radius, and the fluid therefore when it reaches an outer radius from inner radius gains in static pressure, and that change in the pressure energy is given by U2 square minus U1 square by 2. Similarly, the change in static pressure because of the change in the relative velocity, this is again another part of the diffusion. That means change in the relative velocity takes place where VR1 is more than VR2, that means VR2 is less than VR1. So, passage is made in such a way that VR2 is less, is a diverging passage for which the pressure is gained. So, this pressure is gained out of the momentum change or the change in the kinetic energy relative to the blade passage. So, these two, this is due to the centrifugal action, the radial pressure gradient is imposed, I told many times, and this is because of the diffusion from the change in the kinetic energy. VR1 is higher, VR2 is lower. So, therefore, pressure is lower and pressure is higher at the outlet. So, the combination of these two is the static head, static energy, and in this connection I like to tell you again, this is a very important concept for all of you, that in a radial flow machine, so whether it is outward or inward, even if the passage is uniform, there is no change in the relative velocity, still there is a change in the static pressure head because of the change in the U, the peripheral velocity. In case of a turbine, there is a loss in pressure. In case of a pump or compressor, there is a rise in pressure. So, therefore, any radial flow machines outward or inward has to have some pressure change in the rotor, at least by this one. But along with that, if you make a diffusing passage in case of compressor, there will be an additional pressure rise. Okay. So, these two sum up give the static head or static energy. This is very important, I want to repeat it again. So, here what happens, I know V2, I know V1, I know VR1, I know VR2 because all the relative velocities at inlet and outlet is given. And again I know U2, U1 because the impeller diameters are given and the speeds are given. I am not solving this problem, so I just write U2 is pi d2 n and U1 is pi d1 n. N is given rotational speed 1500, 1500 rpm, so that we can 1500 rpm, so that we can do these things. Better I write here. So that U1, U2 I find out, U1 this way, U2 this way we can find out, and then what we do, we can find out the work done. Now, if we know this work done for an incompressible situation, we can write that delta P stage is nothing but rho times this work done per unit mass, work done per unit mass. That means you just multiply with rho, this with rho, you get the delta P per stage. Total in the stage you find out the delta P. Okay, fine. Now, static pressure rise is this one. So, delta P static in the rotor, because this is in the rotor, delta P static in rotor is equal to rho into, let this part I denote at x, rho into x. So, this part is denoting at x, rho into x. So, if you find out this by putting this value, you get delta P the total stage, that means impeller and the diffuser, total delta P stage, because the work is done only in the impeller, delta P total is 221.11, okay, Newton per meter square and delta P in rotor or static pressure rise, static, okay. So, that is static pressure across the stage is 110.71 Newton per meter square. Now, here this delta P static divided by total one is known as, this is the static pressure rise in the rotor and this is the total pressure rise, this is the total energy given. Okay. So, therefore, the degree of reaction in this case we define as delta P stage, delta P static. This already I did earlier, delta P stage. Now, one thing, just 221.11 divided by 110.7. Huh? Oh, sorry, it is just reverse, 110.71 by 221.11, this will be roughly 0.5. Now, here this is very simple, this is numerical, but thing is that what is the concept? Earlier also, if you recall the earlier discussions, that the degree of reaction was defined in terms of the total pressure change in the machine, that is change in the total pressure in the machine divided by the change in the static head or the static pressure in the machine divided by the total head or the total energy given in the machine. And this definition holds true for every machine. In case of centrifugal compressor and axial flow compressor, this was manifested in terms of the enthalpy change, where you considered along with the temperature change. Okay, but here what happens when you consider the flow to be incompressible with a constant density of air and there is no change in temperature. So, therefore, this degree of reaction is better to be estimated by that definition which we discussed in case of hydraulic machines, that delta P static divided by delta P stage. Okay. So, this is the same. So, therefore, we find this. Now, next is the power required. What is the next one? The stage pressure rise, degree of reaction and the power required to drive the fan. How to find out the power required? Power required is very simple. Power required we can write here. Power required is the mass flow rate into work per unit mass. That means work per unit mass is this one, and you can find out the mass flow rate. What is the mass flow rate? The flow rate is 0.6 kg per second. So, therefore, 0.6 kg per second, you know mass flow rate W by M, that divided by the mechanical efficiency. Probably there is a motor efficiency of 80%. That means you write the motor efficiency. That means you write the motor efficiency in the denominator. That means the mass flow rate is given as, in this problem, 0.6 kg per second. Now, W by M, which is calculated, I have only calculated here, I have told you the value of delta P stage. Actually, W by M here, W by M calculated will be 184.26 joule per kg. This is. So, therefore, this will be 0.6 into 184.26 divided by 0.8, which is ultimately 138.19 watt. Okay. So, this is the thing. That means this problem is looked from a different angle, that work done per unit mass is true, that is the Euler's equation. This can be splitted in this term. For an incompressible flow with a constant density, it is better to look upon this way, that this is the static head rise and this is the kinetic energy. Sum of all these three is the energy input to the machine, and that is the total head that is raised in the fluid. So, this is the denominator there per stage and this is the numerator. Okay. So, therefore, the degree of reaction is this divided by this. It was discussed earlier when I discussed the hydraulic machines. In general, this is the degree of reaction. So, this is worked out to be this numerically, delta P stage, which is found out rho times the work done per unit mass. That is the total pressure change in the machine, and the static pressure change in the machine is rho times this part. This is x. Again I repeat, this part, the static head. That means this is the energy per unit mass. This into rho is the delta P static. So, delta P static by delta P stage is this one is 0.5. Clear? Now, after this I will tell you something else, that what is fan laws, because sometimes you will see that people tell about fan laws. What is fan laws? This is a terminology actually. Now, in general for any fluid machines, when I discuss the similarity principles, one of the earlier lectures in fluid mechanics, from all the variables involved in a fluid machines, in the physics of fluid machines rather, I will tell, we derived by application of Buckingham's pi theorem the different pi terms as the criteria of similarity parameters. If you recall that, see my earlier lecture note, then you will find these terms are like this: q by one term is like this ndq, another term is gh by, there are 5 terms, n square d square, another term is rho n d square by mu, another term is p by rho n cube d phi, another term is E by rho divided by n square d square. Now, these are all pi terms. This is let phi 1, this is pi 2. This was told at length in one of the earlier class. There are 5, 4 and 5. Now, when we derive the pi terms for centrifugal compressors, we had 4 pi terms. This is because this term we neglected. The effect of viscosity we did not take. In fact, the viscosity has less effect in fluid machines. Why I will tell you now. Earlier also I told. But these 4 terms we got, but not in this fashion, in a different fashion. I told you earlier in last classes, this is an essence or corollary of pi theorem, that depends upon the choice of the repeating variable. You arrive, number of terms are same, you arrive some pi terms which may not match exactly the pi terms you want or the way you express the result. Then a combination of the pi terms is also a pi term. So, different combinations can be made by making the numbers same, so that you arrive at different pi terms. So, therefore, the pi terms of centrifugal compressors which we derived can be recoupled or rearranged to get the similar type of thing. So, this thing were earlier explained, I am not going into detail of it, but this term I tell you, as you know, this term represents a sort of Reynolds number, because rho nd is the velocity u d by mu. That means this u is the peripheral speed, that means it is a Reynolds number based on peripheral speed. So, it can be changed to Reynolds number based on other flow velocities also. Physically, it represents a sort of Reynolds number. Now, in fluid machines, the flow is highly turbulent. So, in those turbulent flows, the Reynolds number has got very less influence on the flow parameters, mainly in the pressure loss or any other parameter. The Reynolds number does not have much influence. So, therefore, in centrifugal compressors also we have not included the property mu to find out the dimensionless term. So, therefore, in the fluid machines earlier I also told this term is not of that relevance. So, only these terms are relevant. Now, if you take this term, now you see it is not only for fan, for any fluid machines, that if you, now this term is a non-dimensional power rho n cube d phi. This term you know that E by rho is the square of the acoustic speed or speed of sound in the fluid medium relative to the fluid, and this is the square of the peripheral velocity. So, therefore, this is some sort of square of the Mach number square type of thing. So, therefore, you see that now if you see all these pi terms, now you see that for any fluid machines, if we make the fluid machine same machines of same size, machines of same size, then we can tell that Q is proportional to N, because D is same from this pi term, first pi term, which gives Q1 by N1 is Q2 by N2. This is school level things. From the second pi term we see that head, because flow and the head is very important. What is head? This is GH, that means energy per unit mass. Head means energy per unit weight. That means this is the energy either gained by the fluid or developed by the fluid or given away by the fluid, depending upon whether it is a compressor, pump or turbine. H is proportional to N square. That means H1 by N1 square is H2 by N2 square. Similarly, now if we take this term, then we can write power is proportional to N cube, which means that P by P1 by N. That means this is the scaling law, P2 by, that means we are interested in three quantities Q, H and P, and multiplication of these two is this one. So, if it is proportional to N, this is N square, it has to be N cube. That means power is proportional to N cube, head is proportional to N square, Q is proportional to N for same side, and machine of different sizes but at same speed, different sizes but at same speed, one can derive from this formula that Q is proportional to D cube, H is proportional to D square. Obviously, if you know these two, you do not have to see the pi term, otherwise pi term is wrong. That means it has to be D5. That means Q1 by D1 cube is Q2 by D2 cube, H1 by D1 5 is H2 D1 square is H2 by D2 square, and similarly P1 by D1 5 is P2. This is so simple, D2 5. That means the scaling laws with speed for the same size and with size which is represented by the impeller diameter as a representative characteristic size for the same speed is known as, this scaling based on the similarity parameters of fluid machines and valid for all fluid machines. But usually, because this grew like this, that initially the fans and blowers, when they were designed to make the prototype, they used this type of scale. So, till date these scaling laws are known as fan laws in designing the fan. So, therefore, while studying the fans, we must know what is fan law. Fan law is nothing but the scaling laws for the volumetric flow rate, the head, that means the energy per unit weight or energy per unit mass. You can take GH, does not matter, G is constant, and the power with the speed for the same side and with the side for the same speed, and known as fan laws. So, I think today we will stop here, and I like to close the lecture on these fans, blowers, and last class we discussed the axial flow compressors. Before that we discussed the centrifugal compressors, and including all today I will stop, or I will close my lecture series on fluid machines, initially hydraulic machines, basic principles of fluid machines, hydraulic machines, and then centrifugal compressors, axial flow compressors, and the fans and blowers. Okay, thank you.